Section 3.1 is the derivative of a function. So the definition of the derivative, this is one we have been using, and up to this point we've been talking about it as instantaneous rate of change. Now we're using the term derivative. The derivative of a function f with respect to the variable x is the function f prime of x whose value at x is, and there's our definition, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. So we've used this before. We're going to take a look at it real quickly here. The domain of f prime, the set of points in the domain of f for which the limit exists, may be smaller than the domain of f. Sometimes a function has a value at a particular place, but it does not have a derivative there. If f prime exists, we say that f has a derivative or is differentiable at x, and the function that is differentiable at every point is a differentiable function. So a quick example of something that may have a function value or a domain for f but not for f prime would be something that has a cusp. So for this value, let's say it's 2 would be in the domain of the function, but it would not be in the domain of the derivative. So here's an example using the definition of a derivative. I'll let you look through this. We've done this a lot, so you should be pretty comfortable with this. F of x equals x squared. Using our definition, substituting x plus h into the function, expanding, simplifying. They've canceled the x squareds and then factored out the h on top. And once those cancel, we have our limit. Notice that we do need to write the limit as h approaches 0 all the way until the point where I actually put the h into the function to get our final value for f prime. So the derivative at a point, this is an alternate definition, and some of you have used this as well. When we know that we're looking for the derivative at one specific point, we can plug that value in right at the beginning. For this one, we're getting a general equation, and then I can use this to find the derivative at any point. Here, I'm finding the derivative at one specific point only. Let's look at an example of this. Let's say f of x equals the square root of x, and I just want to find f prime at x equals 3. So f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. This is just our slope equation, finding the limit of this slope as my 2 points, x and a, approach each other. So for this one we want f prime of 3. So that's going to be the limit as x approaches 3. Oops, sorry about that. Of f of x minus f of 3 over x minus 3. So plugging in my values, the limit as x approaches 3 of the square root of x, my pen's doing funny things, square root of x minus the square root of 3 over x minus 3. My problem here is that I cannot plug 3 into this. I get an indeterminate form, 0 over 0. So I need to do something to this. If it was a polynomial function, I might factor and cancel. In this case, I have to do something to change how this looks. So what I'm going to do is multiply this by the conjugate of the radical. And I know that you've used this trick in the past. So in the numerator, I'm going to have just x minus 3. The denominator I'm going to leave in factored form. These now will cancel, so I get the limit as x approaches 3 of 1 over the square root of x plus the square root of 3. And now I can actually plug my 3 in, so now my f prime of 3 is simply 1 over root 3 plus root 3, which equals 1 over 2 root 3. So again, I found now the derivative at a particular point. I have an actual value, that's the slope at x equals 3, as opposed to a general equation for the derivative. Notations. We have used all of these notations in the past. Y prime, dy dx. This one we don't use quite as often. It can be used. It's just another form of dy dx. And then d dx of f of x, showing that we're taking the derivative of a particular function. It kind of separates the two pieces as opposed to jamming them together into one notation. Okay, the other thing that we want to look at in this section is the relationships between the graphs of f and f prime. So it says, because we can think of the derivative at a point in graphical terms as slope, we can get a good idea of what the graph of the function f prime looks like by estimating the slopes at various points along the graph of f. We estimate the slope of the graph of f in y units per x unit, delta y over delta x, good old slope. And when we plot the estimates, we will get a function that is our f prime. So let's do a quick example of that. I'm going to do a rough sketch because I did not put graph paper on my slides. I should have. But if this is f of x, and let's make some sort of a function like this. And let's see, 0, 1, 2, 3. We'll say that that peaks at 3, 4, 5, 6, 7, 8. Let's say that that other is at 8. So that's f of x. Let's look at f prime. At 0, I want to estimate this slope. So I want to take a couple of points on a tangent line and see what we have. 1, 2, 3. So let's say we go up 1 and to the right 1. Let's say the slope at 1, or excuse me, the slope at 0, that's what I was calculating, is 1. The slope at 3, we know is 0. 4, 5, 6, 7, 8 is 0. Let's find something in between. So if I do a tangent line here, I don't know why I keep getting lines across. If I get a tangent line here, let's say that that slope is down 2 and to the right 1. So at 5, my slope would be -2. And so I now have, that really should have been steeper because this really should be a parabola, but you get the idea. You've done this before. That should have been a steeper curve there. So that's how we go from f to f prime of x. And that's, again, just an estimate. We have some better methods of doing that once we get more into derivatives. All right, one-sided derivatives, like one-sided limits, a function y equals f of x is differentiable on a closed interval, a, b, if it has a derivative at every interior point in the interval, and if the limits from the right, limit approaching h from the right, h approaching 0 from the right, and the limit as h approaches 0 from the left, right-handed derivative, left-handed derivative, exists at the endpoints. In the right-hand derivative, and we need to know the endpoints because, again, we have set this interval as including a and b. In the right-hand derivative, h is positive, and a plus h approaches from the right. In the left-hand derivative, h is negative, and b plus h approaches b from the left. So again, this is the same as our limits. We say we have a one-sided derivatives. Right and left-hand derivatives may be defined at any point of a function's domain. The usual relationship between one-sided and two-sided limits holds for derivatives. So again, as we said, limits and derivatives have the same rule about one-sided and two-sided. So we can conclude that a function has a two-sided derivative at a point if and only if the function's right-hand and left-hand derivatives are defined and equal. So an example of a one-sided derivative. So this will show that the following function has a left-hand and right-hand derivatives but no actual derivative. So this is the function we're looking at. I hope that you recognize this as the piecewise description of the absolute value of x. Left-handed derivative. So using negative x as h approaches 0 from the left, we get negative 0 plus h minus 0 over h, which gives us negative 1. The right-hand derivative, using positive x for my right hand, we get positive 1. Therefore, this limit, the limits are not equal. The two derivatives, the right and left-hand derivative are not equal, so the function does not have a derivative at 0. And that's it for section 3.1.